Okay, good afternoon, students. Am I audible? Am I audible?
Afternoon, sir.
Yes,
Okay.
sir.
So today our topic of discussion is algebraic structure. So in the other day, we discussed about this set theory and set relation. So it was module 4. So now what we have in module 4 we have this group homomorphism, reading homomorphism, all these things. So before going to in details of this group morphism, so let us discuss about this all this algebraic structure. So we need to know this thing before going in detail. So what is algebraic structure? So have you heard about this term, that is algebraic structure? Anyone? Anyone has heard about this thing, this term at least, algebraic structure? Anyone? Any idea about algebraic structure? Anyone has any idea? Please answer. Am I audible to all of you?
Yes, sir.
So have you heard about this thing, algebraic structure? Have you heard about this term? Please answer yes or no.
No, sir.
Okay, so this algebraic structure is actually we all of us use this algebraic structure in our daily life. So whenever we do some algebra, that is any operation, that is subtraction, multiplication, division, all these things, these are along with this algebraic structure. So all this comes with this algebraic structure. So let us study what this algebraic structure is. So now please tell me that what was the first thing you learned about mathematics? What was the first thing you learned about mathematics, or you?
Numbers. We wrote how to write numbers.
Yes, numbers. So from the very beginning of your life, when you started this recognizing these numbers, actually you started learning this algebraic structure. So at first what you have learned this natural number, that is you started to learn how to count all these things, and this is 1 2 3, you started identifying these numbers. So this is natural number you started learning first, and then you extend this with whole numbers by adding 0 to it. Then you extend this to integers by adding these negative natural numbers to these whole numbers. Then you find out that there is the integers. Then you started defining some operator, that is some operation on it like addition, then subtraction, then multiplication, then division. So when you started doing this all this thing multiplication, then you found that okay, this integer is not complete, there are some other elements also. So these elements are the real numbers. You learn that there are some fractional values are there. So which is actually, if we include this thing to with integer, then we get rational number. Then you started learning that okay, there still this is not complete, there are some equations so which we cannot solve using these rational numbers only, like square root, cube root, like these all these things. So we introduce all these numbers here and add with this rational number, then we got our real number. So this is the whole real number system. That is this is all the real number. That is, we have the real line now. We know the numbers, what are they, where are they, we know all these things. But this is actually not all about this real number system. So when you talk about real number system, always we have some operation with us, like addition, multiplication, subtraction, division, all these things we have with us. And this real number system along with this operation actually form one algebraic structure. So algebraic structure is nothing but a set along with one operation. So here if we consider the real number r along with addition, so this is one algebraic structure. Real number system, that is a set of real numbers along with multiplication, this again form one algebraic structure. So algebraic structure means one set given to you and one operation given to you. This form the algebraic structure, and depending on different property of this operation, whatever is given to you with along with the set, so this algebraic structure has different name. For example, these are the very common notation. We know that set of natural number we denote it by n. Then comes whole number, so set of natural number along with 0. Then integers we write it z, rational we write it q, and if it is real number then we write r. And there is no standard notation for irrational numbers, so we denote irrational numbers by simply subtracting the set of rational numbers from the set of real numbers. So if we subtract this, then we get what we get is known to us as irrational numbers. So now come to this different algebraic structure. So if a set is given to you along with some operations, so depending on different properties of this operation, we have different algebraic structure. They have some different name. And the first algebraic structure which comes in our consideration is groupoid. So what is groupoid? So groupoid is a set along with one operation, so call it star. You may take the star as addition, multiplication, division, subtraction, whatever you want. You can define your own star. That is, you can define this operation whatever you want. So suppose you are given one set and one operation is given to you. So suppose some operation, whatever it is given to you. And if you check with this, that if you choose two elements, suppose a and b, you are choosing two elements a and b from the set what is given to you, and if you operate this given operation, that is star, on this two element, then if you whatever you are getting, suppose your new element is come up after operating the star, if this new element, that is the resultant of this operation, whatever you are getting, if it again belongs to the set s, that is whatever set was given to you, if the new element also belongs to this set s, then we say that this set s along with the operation star is a groupoid. Is it clear? The definition of groupoid is clear.
Yes, sir.
So
Yes, sir.
remember one thing, that whenever we are giving you the star, so in case of this, that means set of this, there are many definitions are there. So say it groupoid. So suppose whenever we are talking about one operation star, so this star is not only stands for multiplication, it star may be anything. It may be addition, it may be some subtraction, it may be multiplication, it may be division, or you may define in your own, like you can say that this star is nothing but the square root. This star is nothing but this cube, or anything you want to define. So there is one example. Suppose you are given the set of matrices of order 2, and you are given the operation addition along with that is this set m2 along with the operation plus. This is a groupoid. Why this is a groupoid? Because if you take any two matrix from this set of m2, and if you operate, that is with the operation given to you, that is plus, then again you get back one matrix of order, right? So that means if you choose any two matrix, if you operate this matrix, that is plus with plus, you will again get back one matrix, that is it also again belongs to this m2. So that's why this m2 along with the addition operation is a groupoid. So there is one example. So suppose you are given the set S, where this S contains the element 1 and -1, and you are given the operation star, where star is the usual multiplication what we know. So that means if we operate this star on this 1 and 1, so what do you get back? You get back 1 again, that is 1 star 1, that is usual multiplication, you get back 1 again. So similarly, if you operate this star, that is 1 into -1, what do you get? You get -1. If you operate this star on this -1 and -1, what do you get? You get 1. So you can see the resultant, that is this 1, this -1, and this one, this also belongs to this set S. So that means this set S along with standard multiplication is a groupoid, right? Is it clear?
Yes, sir.
So now tell me, if instead of this star, that is instead of this multiplication, if you are given addition operation, so would it be a groupoid?
No, sir.
Why?
Okay.
Because
Why?
1 plus -1 equal to 0. So 0 does not belong to S. Also -1, -1, -2 does not belong to S.
Yes, correct. So you have to just see any one, that is you can check only for 1 -1, then it gives you that is 0, which does not belongs to this. You can do with 1 plus 1 also, -1, then -1 also. So but the above is not a groupoid under addition, because this is for example, so you can check with 1 plus 1 also. So because this 1 plus -1 gives you 0 back. So what is 0? So 0, this 0 doesn't belong to this set S. So since it doesn't belong to this set S, so that's why this is not a groupoid. So hope that all of you are clear with it, right?
Yes, sir.
Yes, sir.
So now what we have, the next algebraic structure. So this is a semi group. So what is a semi group? So semi group is just an extension of groupoid. So that means it obviously holds the property of the groupoid, and with the property of groupoid, that is the closure property, we have one added property, which is the associativity property. So that means if a groupoid satisfy the associativity property, that means if you choose three elements, suppose A, B, and C from the set S, given set S, and then you operate this star, that is a given operation, and with this parenthesis, that means which one you should operate first, it matters here. So that means that is A star B star C. If this A star B star C, that means we operate this star first, then the resultant will be operated with this A. So if this is equal to A star B star C, that means here we operate this star first, that is we operate this operation with A and B first, then we operate the resultant with this C. So if they are equal, then we say that the groupoid is a semi-group. That means it satisfies the closure property as well as the associativity property. So that means obviously this is the obvious fact that a semi-group is always a groupoid. So this is a obvious fact that a semi-group is always a groupoid. Is it clear?
Yes, sir.
So there is one example. So we know that in the set of integers, if we have the operation addition, then this associate, that is this operation is associated, hold the associativity property in the set of integers. That means if we choose three elements a, b and c, then if we operate this b and c first, that is b plus c, and then if we add this a, then what we have? We have a plus b plus c. But if we do that, at first we operate this plus with a and b, that is a plus b, and then operate this c, that is a plus b, then plus c, then what the result we get? Both are same. So
Same.
since these are same, so it is, what is it? If they are same, that means what?
The associativity. Associative.
Yes. So that means it is a semi-group. That means semi-group, you have to check that whether this closure property holds. Yes, we know that if we add two integers, then we get back one integer again. So it holds the closure property, and we know this holds the associativity property also. So it is a semi-group. But Z is not a semi-group under minus. Why not? Because you can check your own, you can check any example, you can choose. So here we have taken this 1, 3 and 2. That is, if you check that 1 minus 3 minus 2 is not equal to 1 minus 3 minus 2, because with the this parenthesis we have to do this operation first. So if we do this operation first, what we get? We get 3 minus 3 is equal to 1. So 1 minus
0.
1 is equal to 0. And it is, what is the result? This one?
-4.
Minus
Minus
4.
4.
So 0 not equal to minus 4, obviously. So that means it does not satisfy the associativity property. So that means Z plus is a semi-group, but Z minus is not a semi-group.
Semi-group.
Now we have two examples. That is, if we consider the set of matrices of order 2, and if we have the operation addition, then it is a semi-group. You can check that matrix addition is associative in nature, and it is also closed with addition. Similarly, matrix multiplication is holds the associativity property, and with matrix multiplication, we know that if we choose any two matrices of order 2 and if we multiply these matrices, then we get back one matrix which will be also of order 2. So that means matrix of order 2 along with this addition and multiplication holds the associative property. So they are the semi group. So is it clear?
Yes, sir.
So now we have the next algebraic structure. So what it is? It is the monoid.
Monoid.
So monoid means what? So it should be one semi group first. That means it will satisfy the closure property, it will satisfy the associative property. That means it should be groupoid first, then it should be the semi group, then there is one added property. So which is the property? The property is that there should be one identity element. So what does it mean, the identity element? Identity element means there should exist one element in the set, in the given set S, such that if you operate this set from the right hand side or from the left hand side, you got to get the element back again. That means we have one element E, and if you operate this E with any element A in S, if you operate this E from the left hand side or from the right hand side, then you get back the element again. Then we say that this is a monoid. That means for monoid, you have to check whether this is groupoid or not. If it is groupoid, then you have to check whether it is semi-group or not. If it is semi-group, then you have to check whether there is an identity element or not, whether there is an identity element or not. So if there is, again, if you can find one identity element is there in a semi group, then you say this is a monoid. And from this structure you can check that a monoid is always a semi group, and obviously then it will be a groupoid. Is it clear?
Yes,
Yes,
sir.
sir.
So there is one example. So the example is that you have the set of natural numbers n, and you have the operation multiplication. So you can check that if we add two natural number, then you get back one natural number again. So this is a groupoid. Sorry, we have the multiplication here. So if you multiply two natural number, then we get back one natural number. So it is a groupoid. So in natural number, we know that the multiplication, the order of multiplication does not affect the result. That is, if we choose three element A, B, and C, and if we operate like A into B into C, that is B into C first, and then if we multiply this A, and if we multiply A into B first, then C, then the result will be the same. So this is semi group. And also we know there is one element which is one, we know as notation, we know that if we multiply this one with any of the element from the left hand side or from the right hand side, then we get back the element again. So that means we have one identity element is also there. So that means this is a monoid. Is it clear?
Yes, sir.
So but n plus, that is the set of natural number with addition, is not monoid. Why it is not a monoid? Because there is no identity element. Is there an identity element in set of natural number? So what is the element? That is, suppose you are given one natural number and you are adding some number with it and you will get back the natural number again. So what is this element? What is the element? Suppose you are given one natural number and you are finding one number which by adding with the natural number you get back that natural number again. So what is this element?
0.
Zero. So does this zero belongs to natural number?
No, sir.
No. So since this does not belong to the natural number, that means it is this natural number don't have the identity element. So that's why this is not a monoid. So now what we have? We have the M2 plus. What is the M2? M2 is a set of all matrices of order 2, and we have the operation matrix addition as usual, as we know. So we can check there is the identity element, that is a zero matrix of order 2. So that means if we add this zero matrix with any matrix of order 2, we get back the matrix again. So this M2 plus this algebraic structure is a monoid. So similarly, M2 star, if you consider the usual matrix multiplication, then there is one identity element which is the identity matrix of order 2. So you know that if we multiply this matrix with any of the matrix of the M2, then you get back the matrix again. So this M2 star is monoid again. Any confusion, any doubt?
No, sir.
So now what we learned till now, we have learned groupoid. We extend the idea of groupoid to semigroup. Then we extend the idea of semigroup to monoid.
Monoid.
But now here comes the definition of group. So before defining the group, you have to check whether this is a groupoid or not. If it is groupoid, then you have to check whether it is semigroup or not. If it is semigroup, then you have to check whether it is a monoid or not. If it is monoid, then only you have to check whether it is a group or not. So for group, it must be a monoid with one added property, which is inverse property. What does it say? It say that for all element A belongs to the set, that is given set S, if there exists A inverse, that is if there exists one element which if we operated with the element A, we get back the identity element back. So what is this identity element? This identity element is the identity element of this monoid. So if we get back the identity element of monoid, then we say this element is the inverse of the element A. So if we are able to find out this inverse for each element of the given set S, then we say that the semi group, sorry, then the main monoid will be a group. So is it clear, the definition of group?
Yes, sir.
Is the definition of group clear?
Yes, sir.
So that means if you are given one group, that means it is always a monoid, and if it is monoid, then it is always a semi group, and if it is semi group, then it is always a groupoid.
Group word and also
So
associative.
yes, that is that of the properties. That is
Yes, sir.
each property forms one algebraic structure, and this algebraic structure has different name. So now you
Yes, sir.
have this, that is you have one set G where this G contains the element 0, 1 and 2, and you have the operation star which is defined as A star B is equal to mod of A minus B. So you have to check this set G along with the operation star, will it be a group or not? So to check a groupoid, what we need to check at first?
Uh,
What we need to check? Yes,
Closer, sir, than associative.
Group.
yes, closure property. So that means what are the elements we have? We have the elements as 0,
1, 2,
1 and
2.
2. So we can draw this table. So this is 0, 1, 2. We have 0, 1, 2, and we have star. So A star B means mod of A minus B. Just tell me what is 0 star 0,
0,
0 star 1,
0, sir.
0,
No,
One.
sir, not
1,
multiplying. Yes, sir. Yes, sir.
0
Sorry.
star 2,
2, sir.
2. Then
1.
then
Again 1, sir.
1 star 1,
0.
1 minus 0.
Acha, 1 minus 1.
Then
Sorry.
1,
1.
then
2,
then
1,
1.
1 and
then
0.
0.
0.
So that means if we choose any two element and we operate this star on this element, so what we get? So these are the resultant, that is 0, 1, 2. So these are the resultant. So does this element belong to the set G? Does this element belong to the set G?
Yes, sir.
So that means this G along with the operation star is a what? The first one,
Closer, sir.
closure property it
Groupoid.
holds, groupoid. So this is a
Closer
groupoid.
first property.
So now what is the second one?
Semi group.
Semi group. So to prove it semi group, what we need to check?
Associativity.
Associativity. So that means we have to check that whether A star B star C is equal to A star B star C or not. So does it hold this?
Yes, sir. In case of addition.
It holds?
No, sir.
No. So example, so let us do this thing. 1 star 1 star 2. So what is 1 star 1?
One.
0.
One
So
star.
then 1 star 1 0, right? Right or wrong?
Yes, sir. A minus
1
B.
star 1 is 0, right? So 0 star 2. So what is it? It is 2, right? So now what we have? We have 1 star 2. So we just change the parentheses, the position of the parentheses. So what is the 1 star 2?
One.
So we have to
1.
do this operation first. 1. So what we have? We have 1 star 1. So what is 1 star 1?
0.
Zero.
So does this 2 equal to 0? Is 2 equal to 0?
No.
So that means
No.
1 star 1 star 2 not equal to 1 star 2. So that means this associative property does not hold there. So since it doesn't hold there, that means this is not a semi group. So since this is not a semi group, so there is no question of checking the group. That is our other property of group. That means it is not a group. Is it clear? Is it clear?
Yes, sir.
Although you can check that here the identity element exists, because if you operate this 0 with any element, then what we get, you get back this element again. That is, you can check if you operate this 0 with this 0 1 2, you get this, you get back this 0 1 2 again. So this side from the, this is from the left hand side, this is from the right hand side. So if you operate this 0 with this 1 0 1 2, you get back the 0 1 2, these elements again. So that means the 0 is the 0 element here, that is the identity element here. So that means it has identity element, and you can check that each of the element is its own inverse. So each of the element is its own inverse. That means if you operate this a star a, that you get back the 0 element, that is identity element. So the identity also exists, inverse also exists, closure property also holds, but the associativity property doesn't hold. That means it is not a groupoid. Am I clear?
Yes, sir.
So there is another example, that is you have the set of matrices of order 2 and you have the usual matrix multiplication operation. So is it a group? Is it a group? The set of matrix of order 2 along with usual matrix multiplication operation. Is it a group? Is it a group? Yes or no? Is it a group? Is it a group? The set of matrices of order 2 along with the matrix multiplication.
I think yes.
Yes, sir.
It
Yes,
is a
sir.
group. Okay, so you have checked that it is closed, right? You have checked it is associative, property hold, associated property hold. You have checked that there is one identity element, that is the identity element, that is identity matrix of order 2, that is 1001. Have you checked the inverse? Does the inverse exist for all the elements?
Yes, sir.
Yes. Okay. So suppose
No,
you
sir.
have the matrix A,
Inverse hold
which
no.
is in general given by A, B, C, D. But
When
if you try to find out this inverse, then what we get? You get the inverse is adjoint of A divided by mod of A. That is determinant of A. So what is determinant of A? That is AD minus BC. So if for this element, this A, B, C, D, if it is 0, then does the inverse exist? Then does the inverse exist?
No, sir.
So that means for all the elements, the inverse does not exist. That means this M2 star, that is this M2 along with the matrix multiplication, usual matrix multiplication, is not a group, right? Right? Am I clear?
Yes, sir.
So for example, one matrix which don't have any inverse in this M2 star group, so that is 2142. You can assume any other matrix also, you can check. There are so many matrices whose inverse does not exist. So that this matrix is 2142. So this for this matrix the inverse also not exist. So next is our abelian group. So what is abelian group? So abelian group is a group, that means it should satisfy all the four properties of a group. That is, it should be a groupoid at first, then it should be a semi-group, then it should be a monoid, then it should be a group. So that means all four properties of the group hold there. Then there is one extra property. This property is the commutative law of the operation. That is, if you have chosen two elements, that is A and B, and if this A star B is equal to B star A, this holds, then we say that this is a commutative group or an abelian group. So that means if in a group, if the commutative property holds, then we say that the group is a commutative group or an abelian group. Am I clear?
Yes,
Am
sir.
I clear? So that means obviously by definition, if you have a group, it should be a monoid, it should be a semi-group, and then it should be a groupoid. For example, suppose you have the set of integers z, and you have the usual addition operation, then this z plus is an abelian group. We know that if we add two integers in which direction we don't know, that is if a plus b will be always b plus a, so this the ordering doesn't matter. In r star, that is in multiplication, usual multiplication in r, in real number, this is also commutative. That is in which order we are multiplying, that is ab will be always equal to ba. We know all these things. So that's why this z plus and this r star, where star is the usual multiplication, is an abelian group. But suppose you have the group that is GL2. So what is this GL2? So this GL2 is a set of all matrices of order 2, excluding the matrices whose determinant is 0. That means we exclude the matrix, that is, we exclude the singular matrices, because in the earlier example we have seen that this whose determinant is 0, that was creating the problem for the M2 group to be a group. For the M2 star algebraic structure to be a group, so we just remove this whose determinant is 0. That means we remove the singular matrices, and now what we have? We have GL2 star. So this GL2 star is a group. Is it a abelian group? Is it a abelian group? Is GL2 star, where GL2 means a set of all matrices whose determinant is not zero? So is this GL2 star an abelian group? Will it be an abelian group?
No, sir.
Why?
It's a property.
Which property? Which property?
It's a fifth.
Fifth property.
Yes,
What it was? Commutative,
it's
right?
yes, sir.
So what does it say? It said that if you choose two elements, that is A and B, so with this star operation, it will be A star B will be equal to B star A.
Sorry, yes, sir.
So that means we know that in matrix multiplication, A into B is not equal to B into A, right?
Yes, sir. Yes,
It may
sir.
not hold. So that means this we have, if we have to prove this, then we have to choose two example, that is you have to choose two matrices to
Matrices.
show that. Yes, so here I have chosen two matrices arbitrarily. You can choose your own. You can choose your own. So that is I have taken here 1 3 t 1 3 2 minus 1 and 2 minus 1 0 2. You can you can choose your own. So you can check that this AB gives you 2 5 4 minus 4 and BA gives you 0 7 4 minus 2. So that means this AB is not equal to BA. We know this thing, that is it is not hold. It doesn't hold. That is the multiplication is not commutative in matrix operation. So that means this GL2 star is not an abelian group. Is
Abelian.
it clear?
Yes, sir.
But you can check that this GL2 star will be a group. Okay.
Yes,
So
sir.
that is all for today. So is there any question, any doubt?
No, sir.
No, sir.
So which group is this? Which section? IT, right?
Yes. Yes, sir.
So now I have opened your attendance form. So just give you attendance, go to your Google Classroom, click the attendance form, give your response and submit. And one thing I want to say you that I may need some extra classes, because you know that I have started 3 weeks later. So if I need some extra classes, so I may call you for extra classes. So that's why I need the information that when you are free actually. So I know that from 10 a.m. to up to 3 p.m. all of you are busy with the classes. So are you free after this 3 p.m. and 4 p.m.? Are you free, all of you? Is there any
So we are
class?
free from 10 to 3 also. Sometimes we are not having classes. So you can take class.
Okay, so you can tell me that which are the times at which time you are free.
So we will discuss once because some of our students also uh, do some courses. So we'll discuss once and inform you.
Okay, okay. So that is fine. And I guess that you are also free from after 3 p.m. also, right? You are also free, right?
Sir, not getting the link for attendance. You can write here, sir.
You are not getting the link.
Yes, sir, for attendance.
Many of the students have already given the attendance.
But sir, I don't have, sir.
Are you in the Google Classroom?
I don't think so, sir.
अरे नीलेश ग्रुप खोलो ग्रुप में भेज दिया है
अच्छा हाँ हाँ ठीक ठीक थैंक यू
Okay, so I guess that all of you are also free from 3 to after 3 p.m. and also you are free in Saturday, right? So I am not sure that whether I am taking the class. I just want to ask you, are you free at that time? Who is seer here? Who is seer?
So Ritika is CR. She left. She left, I guess.
Okay. So are you free in Saturday also? Is there any class in Saturday or do you have any problem in Saturday? Do you have any problem?
So in weekends, I have some problems in my family, my personal problems.
Okay, so you
Weekend.
can't do class on Saturday, right?
Yes, sir. Saturday, Sunday I
Okay.
can't do.
And if I take class after 3 p.m. then do you have any problem? Yes, do you have any problem?
No, sir.
Okay, so I am just noting it down. So if I need extra class, then I will contact your CR and I will tell you. Okay. So this is all for today. So
Okay.
thank you.